Thank you. It's a pleasure being here with friends and on this special occasion for Michael. So I like this picture. I think it gives a good spread of Mike. He's not looking at the problem like this. Okay, we get this view of the problem. Now, I heard on Zoom Nati Zeiberg's talk, and many things were the same, except also for me, he's more or less the young, promising postdoc, which I remember. But this is more or less the picture which, when I think about Mike, that's usually what comes to my mind. Occasionally he grows up a little, but that's about where he stays. Now, Nati was saying that he would characterize Mike by the word brilliant. And I already had the transparency, so first I was happy that I didn't write brilliant. Otherwise I would have to explain that I'm not copying Nati. But I think actually that brilliant, many of you are brilliant. The issue is not the brilliance. To me, Mike is unique. Unique in the collection of properties that he has, some of which I will briefly mention, and most you know anyhow, and I won't mention. He will blush too much even with the mask. So, the first thing when I actually met, my first memory of him is a sparkle in his eyes. Very, very intense, very, very interested, at least for a moment. Then depends what he hears. But in the beginning, you see this enormous intensity, this curiosity, and from very early on, the attempt to actually grasp the big picture and never be satisfied with just one or two details which you give during a talk. And that even when he was working on C smaller than 1 systems, which definitely were not the big picture, but definitely he was also very curious then on the big picture. Now, to make our life easy, he followed Churchill. And as you know, there is this claim that Churchill said, history will be kind for me because I intend to write it. Then there are others which give the quote above, which claim is a true quote, but it's a small deformation of the shorter, terser quote. And if you read the lecture he gave for Mumford, which is called From Algebraic Geometry to Machine Learning, you actually already get a feeling of the history of Mike from when he was a student, what interested him, what were the various branches he had before, and what he chose, what were the roads taken and what were the roads not taken over the years. So I invite you to look at it. Then you can go back to his PhD thesis, which I didn't know about actually, till I wrote the paper. And by the way, one general lesson over time is that as you give talks in such occasions, you find that you are talking mostly about yourself. And I noticed it with other speakers which already gave talks before. So I think here, please note that I waited till this moment to inject myself into the talk. So indeed, Mike did a very interesting work. That was his whole thesis on G over H models under John Schwartz. And in there, let's say, I'm still bringing out the line, what he thought. He was still thinking on what are the most important problems. I'm not sure he will say that still today, but the 3 lines below, he injected in his thesis what he thought was the most important problem at the time. Then we both share sat on the same chair on various times. So that's an honor and a pleasure to sit with the same chair with Mike. Then the last thing, I would like to tell you about something I learned from Mike and impressed me very much rather recently in a very cold, for me at least, New York night. So we were sitting and discussing various things. And one of the things we were discussing, as we are, after all, these cavemen living within constraints of various kinds and trying to observe the whole universe. And then he gave me more or less the one-liner. We were discussing physics and its future, and he says, look, let's face it, we have only one universe to experiment on, and there's only so much you can learn from one sample. Bye-bye, guys. Doing that stuff. And that type of insight remained with me, and I'm afraid I can't ignore it. But on the other hand, we have only one universe. Then I would also say, without any details, that behind the facade there is a very kind and generous person. And these are various hints to where this generosity went to. Okay, after this introduction, I'm going to physics. The topic is, how should I say, can we visit, for example, can we build a space module so we can visit the sun? In other words, can we surround ourselves with a solid, and this solid, even no matter how high the temperature will be, will remain what it is. And therefore we can go deep and visit the sun. And one of the reasons I chose this is not only recently I was interested in that subject, but because Michael spent quite some time on large N models. And here the features are strongly influenced, at least as far as we know, by the fact that we have the large N. So I'm going to discuss this work, and the work was done with the collaborations, Noam Chai and Sumyadip Khachuri in Jerusalem, and Chaghar Choi and Zohar Komargotsky from Stony Brook, and Misha Smolkin in Jerusalem. Okay, now I start with something which for me is an idea fix. Okay, it's something which I'm stuck with since it first occurred to me, and I can't get rid of it. So I'm sharing it with you as well. And the issue is the properties of the vacuum energy in conformal field theories which have flat directions. So as you know, you could phrase the original Zeldovich problem in a very simple way. There are now much more sophisticated and more subtle ways to do it. And ignore gravity, forget that. Just ask a question in quantum field theory about the vacuum energy. Assume that you are in the 40s. You understand everything. You know there are protons. You know there are electrons. You know there are photons. You can study the system at Rydberg. You know what are the elementary particles involved. And you look at the low energy effective theory. You cut it off at Rydberg. So you would estimate that the vacuum energy should be of the order of the cutoff to the force. And if then you do try to relate it to the vacuum energy as seen in gravity, then you would say there is a very big problem. Now, for my mind, that statement, which is again the most primitive way of expressing, and I think the original way of Zeldovich, except with a different scale, to look at the problem, has in it one loophole. And the main loophole is that when you do effective low energy theories, you always have to remember, and Weinberg remembered that when he did pion scattering, doing low energy, you need to remember all the symmetries in the model. If they are spontaneously broken, or if they are not spontaneously broken. You need to have all of them involved and all of them there, and if not, then you can draw some conclusions at your own risk, but they may lead you astray. So the claim is that in conformal or scale. I'm not differentiating here between scale and conformal invariance. I'm taking them to be the same. The value of the vacuum energy does not depend on the scale on which scale invariance is spontaneously broken or not. It has no relation. It's a scale in the problem, but it's not related to the vacuum energy scale. So the scale of the symmetry breaking does not affect the vacuum energy. Okay, that's a general statement. Now you want to go to specific models and see how it works. So the first time I saw this occur was in work done by Bardin, Bander, and Moshe. If you phrase it in this language, you could say the following. Look at the model in 3 dimensions of space-time. Look at the model which has just one marginal, classically marginal operator, which is phi to the 6. Make an ON model, so it's a vector ON model, and take a certain order of the limits. It's very important, the orders of the limit here. You first take n to infinity, and only then you remove the cutoff. Okay, so this is, you look at the set of diagrams which survives when you first take n to infinity. In that case, you see that the coupling of phi to the 6 is not just classically marginal, but is a truly marginal operator. And you find that the beta function of that theory vanishes. Again, this is not true in the opposite order. But in the order of limits that I told you, that's what happens. Okay. Now, what consequences do we get from that? So you can look at it from the following point of view. Let's do it. There is an exact calculation which you can do, and was done. I will tell you at the end what it was. But before, let's do a Gedanken. Let's do a sort analysis of this. So the sort analysis is, let's build the effective potential. We have the coupling is real because the beta function vanishes. So there will be doesn't have a scale. You don't need to introduce a renormalization scale because the beta function vanishes. So the effective potential will be some function of the coupling, and it would be multiplied by the scale in the problem, and the scale in the problem would be the ON invariant, which is phi squared, and that field has dimension, phi has dimension 1/2, and therefore this all together sigma cubed has dimension 3. So this is the general form that the potential could have. Then you can do the calculation and see what f of G6 indeed is. And that it's going to be something.
Sorry,
is there other...
I mean, the phi square requires normal. There is a claim it can be.
So we skip it. But no, the issue, is this,
the absolute value.
Is it fixed? Yeah. Okay. You're talking, which is true, that if you do dimensional regularization, in dimensional regularization, you find that indeed phi squared can in certain number of dimensions be negative. Depends if in 4, in 3, and so on. But I don't want to discuss. This is, had we discussed this model in great detail, I could have shown you how everything works. That's not a problem in all the analysis I'm telling you.
I see, because Bardin et al. Were arguing there is an instability beyond the given coupling because of the...
No, it's because of the form of f of G6. You're too... Okay. Too knowledgeable, but not remembering exactly. So that was the... Yeah, okay. So again, we don't know what f of G6 is at this moment. We're just doing a general analysis. So the general analysis is the following. Let's say that we have a G6 such that f of G6 is positive. In that case, what would we say about this model? The expectation value of sigma would vanish in the ground state. There would be no breaking of scale invariance, so no spontaneous symmetry breaking. The masses whatever that is in a conformal theory, you would call 0, and the value of the potential, the way you've written it, vanishes. What happens if you have f of g6 negative? Well, in that case, actually, the theory is ill-defined. It doesn't have a ground state, and actually it can't be resuscitated. It's just a theory that is ill-defined, and we leave it alone. And here, because I'm talking to a connoisseur, what happens in this model that f of g6 essentially has the form 1 minus g6. So when what happens is the problem is not from phi squared. The problem is that when g6 is larger than 1, f of g6 becomes negative. Okay, but again, doesn't matter now in the general analysis. Okay, but then you can come to the interesting case. The interesting case is if you have an eigenvalue, let's call it, when there is a value of g6 for which f vanishes. In that case, the effective potential would be 0 in any case. It would be, no matter what phi sigma cubed is, it's multiplied by 0. So in that case, there are two possibilities. You could have taken the sigma to vanish, or you could take it not to vanish. If it vanishes, we are back to the case when f of g6 was positive. It's the same analysis. If, on the other hand, it does not vanish, then you can see that you have broken scale invariance. You will see that particles do acquire a mass. And on the other hand, there is a massless ON invariant object, the dilaton. And the potential continues to vanish. It does not depend on sigma, which did acquire an expectation value. So in this case, you see an example. And this example we looked at models of the type ON cross ON to have more structure, because the point where I did cheat here, there was one point I cheated. I did not allow in the model a spontaneous breaking of ON symmetry. Had I allowed the spontaneous breaking of ON symmetry, there could be also, the effective potential could also have depended on that expectation value. You do the analysis and you find out that in a single group that doesn't happen. So that phase does not exist. However, if you have ON cross ON, there is a potential also to break the ON symmetry, one of them, both of them, and in that case there is more structure to the model. You have conformal manifold already and so on. However, the main issue is the vacuum energy does not depend on the scale in which is there. And that's, again, not what we usually intuitively say. Imagine you are giving a class, you will talk about pion theory, you would say that the vacuum energy should be F pi to the force. You would always associate the scale of breaking with a low energy effective theory contribution to the vacuum energy. And in a conformal field theory, there is a scale which doesn't have anything to do with that. Okay, now this example is not supersymmetric, that is nice. However, it's in 3 dimensions. What about, are there any theories which have the same property in larger than 3 dimensions? And en passant, in this work done here, we will find that in all dimensions, there are examples between 3 and 4, till 4 minus epsilon where the phenomena occurs. And I will share them. Unfortunately, in 4 dimensions, that will not happen anymore. And it means the examples that we had don't work. There are interesting things which happen in 4 dimensions, which I'm now going to describe, but it's not going to be the flat direction. So this was my fix, and it's still something which I would like to understand. Is there a no-go theorem which says that non-supersymmetric theories in 4 dimensions, for example, cannot have flat directions? The flat directions I will describe in fractional dimensions occur even for large and not infinite n. They occur also for infinite n, but not only for infinite n. Okay, so now to justify the title of the talk. So as we have a general audience, so spontaneous symmetry breaking of global symmetries is a very important role. In general, in physics, such phases are typically determined, their characterization determined by some value of an order parameter, and in most cases, when that order parameter, let's make a zero form order parameter. When that order parameter vanishes, then you are in an unbroken phase, disordered. When it's not zero, it's an ordered phase. And the value of M is determined in general by the minimum of the energy or the free energy of the system, depending of zero temperature or not. So the free energy in different phases, we can have, in this situation, symmetry is unbroken. In this situation, symmetry is broken. It's here, when the symmetry is broken, there was a maximum actually at the origin. You can have a metastable at the origin and nevertheless still have symmetry broken. Okay, then at different temperatures, the free energy can behave differently, and we discussed that the most trivial case would be one where the global minimum lies at m equals 0 for all temperatures. In that case, the symmetry is unbroken persistently, and this one expects. Another case is when the symmetry is broken at low temperature, but gets restored at higher temperature. And this we expect intuitively. And the intuition comes from the following. You say more or less, there is some energy stored in this, in the vacuum by the fact that you gave an expectation value to a field. The moment the average energy in the system or the temperature is large enough, you think that this is already irrelevant. And by that time, the system doesn't care that there was this very small contribution to non-trivial energy. Anyhow, there's a lot of non-trivial energy and the symmetry will be restored. That's our expectation, and that really usually happens. So these transitions where the symmetry is restored are usually first order or second order transitions. So a first order. Okay, another signal from above. So, what am I doing which causes?
Maybe you might have a fold.
Beg your pardon?
We could have fold.
Not on me, it's there. Okay, so here we have the example when you have a first order phase transition when the symmetry gets restored, and here you see the free energy when it has a second order transition when the symmetry is restored. Okay. Now, there are also symmetries where it's known to have system where what is called inverse symmetry breaking happens. Namely, you start in a temperature 0. We start at a temperature 0, and you find out that you have a situation where symmetry is unbroken, and you raise the temperature and it gets broken. Okay, this could be, for example, a situation you move from here to here, then there will be an intermediate region for where the symmetry is broken. You would raise this temperature again, and this would be restored. And this is what happens, for example, in Rochelle salt. It's a typical example of such a situation. Okay, but Steven Weinberg always liked to challenge dogmas, and actually Landau before him already challenged the same dogma. And he was asking, okay, is it obvious that always the symmetry will be restored? That is, there will always be a temperature high enough for which the symmetry will be restored. And he looked at phi to the fourth theory in 4 dimensions. he considered series which had Z2 cross Z2 symmetry and series which had ON cross ON symmetry. And with one, the question, if you treat the series with one group, no structure. You need to have two groups for that to happen. So if you have it in ON cross ON situation, you see that in situations where the coupling G1, 2, so let's say there are two fields. So you can have here a term phi1 squared, phi2 squared, and you can have phi1 squared, phi2 squared, and then you can have phi1 to the fourth, and you can have phi2 to the fourth. So in a situation where G1, 2 actually does not vanish, then there are situations when the symmetry is spontaneously broken, and not only it's spontaneously broken, but it is not restored. Again, a single group does not exhibit this, and this thread will remain. And I don't understand why, or we don't understand yet why, but that thread will remain. However, it does break in that case. And this was a paper written in '74, which, when I read it first, always intrigued me that this actually occurs. Now, of course, the problem is with that these series are not UV complete. So what does it mean, high temperature? How do you, let's say you do the series with a cutoff. So how high do you allow the temperature to be at a given cutoff? And how can you make sure that this continues to make sense? So this remained a problem. It was from time to time, because physicists don't like to be told things cannot happen, so they always try to find, and actually many of the most interesting works are finding loopholes in claims which say you can't do something. But at the time before our work, all these suffered from the fact the examples were not UV complete. Okay, so what we decided with the group of authors I described in the original, one of the original slides, is to look at this, but solve the UV incompletion by taking a UV complete theory, namely a CFT. Now, and this will be done in fractional dimensions and will be done at dimension 4 with other types of groups with a gauge group. Okay, so what is the advantage of doing this for a CFT? That if you are in a situation where the symmetry, let's say, was broken already at 0 temperature, or even if it was not broken at 0 temperature, the moment you look what happens at finite temperature, you will get a result which is either valid for all temperatures. I mean, the result will be valid for all temperatures. Either the symmetry will remain broken for all temperatures, or it will not be broken for all temperatures. So you don't have to worry that but the hard part is to find the CFT on which you can do this exercise. So this was the approach, and the first group of works involved only scalars, and we were looking at the Wilson Fisher-like CFTs in fractional dimensions. Now, actually, Slava Richkov is not here, otherwise he would immediately have jumped and said, well, you know that it has been discovered in recent years that such theories have some operators in them, sometimes of very high dimensions, which are complex, and therefore it's not obvious if these theories don't have other defects. And that remains true, and this will not be changed by what I say. When we study 4 dimensions, of course, this will be removed, but then the feature of persistent symmetry breaking will remain. What will be lost is the fact that it can happen also for very large but finite n. There it will remain only for, at least what we know, only for infinite n. And the other point which is going to be missed from my point of view is the flat directions, because the flat directions occur here in non-supersymmetric series. Okay, so now what groups to study when we have the Wilson-Fisher points? Well, we study groups ON1 cross ON2. A single group, again, will not exhibit the phenomena I will discuss. One can do the analysis for a single group. You're welcome to look at the papers. What happens for a double group doesn't happen there. So there is no persistent symmetry break there. On the other hand, if we take the limits where these ends I will discuss a case when they're equal, I'll discuss the case when they're different, then you do have very interesting patterns, and some of them persist to finite n. I will also, at the end, as much as I have time, I will mention the four-dimensional large n gauge groups, which offer you a persistent symmetry breaking. I think it's interesting just to know on their own. Again, Nati, when he described his talk, said, well, you know, when you have a phenomena, you give the simplest example, but then you lose some of the structure, given the time. So the same actually applies here. And I will also mention that in such theories, you find that you can have marginally relevant deformations which are constructed only out of scalar operators, which is not something, the usual thing that happens. And you can exhibit there, you can also see with them the symmetry non-restoration. You will see the breaking in the infrared, and then you will see the non-restoration afterwards. So they will have this type of structure, which is not the usual structure of phase diagrams we have. Okay, so now what are the common features of all these theories? So both there was a mistake. Where am I? So okay. What is the common feature of these models, both the four-dimensional gauge series and the fractional ones? They have two sectors. As I said, with a single group, it doesn't work. In the case of a gauge group, then each sector has its own global and gauge symmetry. For the fractional dimensions are just global symmetries involved. The matter in each sector transforms under the global, and in case there is a gauge symmetry group corresponding to that sector. And the two sectors, something that my chairman loves to do, are weakly coupled. Then, in addition, there is a weak coupling between as I said, between the two sectors. This structure seems to be necessary, again, to get the persistent symmetry breaking. And up to now, all models that exhibit this persistent symmetry breaking, did I say that already? Have this structure. What happens in 4 minus epsilon dimensions? How long now? I have to make a decision on how to rush through.
You have another 15 minutes.
15?
Yeah.
Okay. Okay, so let's look now at 4 minus epsilon dimensions. These are the fractional dimension. So we have two scalar fields, phi1 and phi2, one of them having m component, one of them having n minus m components. Okay, and we look at the action of this symmetry system, and we are looking. There are various limits we discussed. I will interchange the discussion now. Epsilon, sometimes we take epsilon to be much smaller than 1 over n. And n can be finite, but very large. And sometimes one first takes n to infinity, and then epsilon one tries to take all the way to 1. And actually, the difficulties at 0 are obvious from this because it's a scalar theory. But you also encounter zeros at 1. So you can't, problems at 1. So you can't extrapolate neither to 4 nor to 3. The results are between 4 and 3. Okay, so let's begin to discuss the features which come up. What happens when the groups have equal rank? When the groups have equal rank, and in addition, let's first, for this discussion, set n equals strictly infinity. Then the model, although not supersymmetric, has a conformal manifold. The conformal manifold is defined by the determinant of the couplings to vanish and to sit on a circle of a radius which depends on epsilon, where epsilon, I remind you, was a deviation from 4 in the theory. So we have here a conformal line. Each point here is a conformal theory of that problem. Now on top, once you sit at each of these points, you can ask what is the effective potential of the model at that particular set, for that particular set of couplings. And it turns out that the minima are given in the case when G12, the coupling between the two, is negative, that there is a non-trivial effective potential, and that effective potential actually has a flat direction. And the flat direction is parameterized by some scale, because the fields carry a scale. So this scale we call mu times this ratio of the couplings. That's the direction of the flat. That's the flat direction. So maybe it's better just to show an example. So this is a temperature 0 equal rank. And this is how the effective potential looks like. I think you see here this line. That is the line on which you have a flat direction. So you have a theory now above 3 dimensions, which has in it a flat direction, and the vacuum energy would vanish along all that, no matter how you broke the scale symmetry. And you can do the analysis. You can find the pions in the theory. You can find the dilaton in the theory. So you can see that these words, which are obvious from the structure of the effective potential, actually materialize in the Feynman diagrams of the problem. Okay, so this was one of, at least as I told you, it gets stuck at 4. But so this is like Moses. You're allowed only to the Jordan River. You are not allowed to cross the other side. But at least you get till there. So one is very near, and one hopes that eventually maybe either show a no-go theorem or cross the river. Now for t non-zero, again, something very surprising happens, not something that I expected. Namely, the flat direction remains. I did not expect, I thought I'm putting a new scale in the problem. There would be no flat direction. But the flat direction actually remains, and again, best to show the pictures. So what happens is that this time, it's the opposite than what you asked me originally. You find that there is a hole, and that the expectation value of phi squared actually cannot be below a certain number. So when you look at the effective potential, you see that there is a hole in the field space, which reminded me something, again, sorry, Nati, but I thought that was either for n flavor equal n color plus 1 or something. He had suddenly in moduli space, a hole was created there. So again, a hole is created here. And the moment the hole is created, it means that you will have spontaneous symmetry breaking. That means you don't even have the option to sit at the center. Remember from the first example, you had the option. You could originally, at t equals 0, decide you sit at the origin, and then there is no breaking. And then you could sit away from the origin. But here you can't sit at the origin. You have to sit away from the origin. Okay, and on this.
What do you mean a hole, Eliezer? So sigma starts from some value.
Yes, yeah.
And how does this come about? In the potential?
This I won't explain now. But we have to go through the paper and see the whole details of it. It's a surprise. It's not something I would have expected. Okay? But that's what happens. So this again is a flat direction, and you notice that the flat direction doesn't start at the origin. The flat direction starts at a place where already one of the phi's is different than 0. Okay, now this was equal rank, and one can take finite n corrections to that. And actually, some of the structure remains. However, the bottom line is that in the equal rank case, in the presence of finite n corrections, there is the symmetry breaking the persistent symmetry breaking is not persistent. You lose the conformal manifold. It doesn't being a continuous manifold, it becomes 3 points. And the 3 points, when you analyze each of them separately at finite n, you always find symmetry restoration. So that doesn't work in the case of equal rank. And that will conclude that. On the other hand, when we do that was a disappointment, but then we went to do unequal rank. And when you do unequal rank, what I said now does not happen. So maybe to conclude that part, equal rank, infinite n, you have persistent symmetry breaking. However, the moment you put equal rank and allow the first large n correction, this doesn't happen anymore. You lose almost all the conformal manifold. You remain with 3 points. And when you look at those points, you don't have persistent symmetry breaking anymore. Okay, in the unequal case, now the structure is a little different. It's a renormalized circle or an ellipse. It's here. This is a ratio between G11 and G22 that you have to have, and this is the epsilon. And in this case, when you take the infinite n limit, you find out that when G12, indeed, when it's negative, you find out that there are flat directions. You find out that there is, at t equals 0, there is symmetry breaking. And then when you increase the temperature, it's persistent. The symmetry breaking continues. And again, it's the same type of picture. When you have t equals 0, you have a flat direction, and the flat direction goes through the origin. And that's a flat direction. But the moment you raise the temperature, the flat direction remains, but it starts at this value of the field phi squared, and you have persistent symmetry breaking. So again, these were two surprising results. I did not expect at finite temperature to see a flat direction. And nevertheless, in the large n, it happens. And then when you do finite n corrections, it's a little more complicated here. But here, when you finish the analysis, the result survives. Also for finite n in a certain range of the question is how unequal are the ranks? And this is the parameter x, which appears here. And you can find out for what regions you have persistent symmetry breaking, also for finite n. So then, as I mentioned, there is a problem with unitarity when you are in fractional dimensions. And I won't enter into the details, sorry, also here, Kostas, but when you try to push to d equals 3, this does not work anymore. So this is only for epsilon between 0 and 1. Okay, so the summary so far, we found an example of a model in fractional dimensions which demonstrates symmetry non-restoration. So all you need to do is find this material, live in fractional dimensions, and jump to the sun, and you can go deep, and it's okay. You can see what's happening there. Then I told you that when one of the groups, when they're not equal ranks, then you find out there is a conformal manifold, there is a flat direction, also at non-zero temperature, not supersymmetric, and this happens for finite, also for finite n in some examples. And I remind you again, the key ingredient was that once you do study a CFT, everything either happens or doesn't happen at all temperatures. So we use that feature. Okay, so now we come to the last part, just to let you know that such a model exists, or it's such classes, there are an infinite class of models exist. So going to 4 dimensions to have a CFT, we need to have a gauge, theory. And again, you can do an analysis and try with 1 gauge group, and we proved that it doesn't work. And then we went to 2 gauge groups, and actually each of the gauge groups was already itself 2 gauge groups. So actually we had 4 gauge groups in the analysis. And first you have to identify CFTs. So to get CFTs, we tried to, what we did is we considered the Banks-Zaks fixed points. That is, we took both the flavors and the colors of the different representations to their number to infinity in a fixed way, so that you can have a fixed point. And we found that there is a conformal manifold in these models. And as I said, this time when you look at temperature 0, there is no flat direction, but there is a persistent symmetry breaking, which happens on a subset of the conformal manifold, which you identify. And so what do you need to do for this? So for this, you need to be able to show how the symmetry breaking, you need to identify the conformal manifold. You need to see how the symmetry breaking occurs. And for this, you need to identify some global symmetry which breaks. And en passant, because you have a gauge group, you will also remain in the same Braut and Laird-Higgs phase, but in these models, you have particles in the center of the group. So therefore, the phase transition anyhow is not clear from the point of view of the gauge particles. But from the global symmetry, you can identify and see the breaking. Okay, so these are other decorations of that. Maybe I will skip those. Okay, so and just say more details about the model. So the model has 2 groups, and each group is built out of a product of 2 groups. The groups can either be SON or SUN. So you can have SON1 cross SON1 times SON2 times SON2, and there are particles in both the gauge representations of the gauge group and the flavor group. Both bosons and fermions, but the theories are not supersymmetric. Then you can do the same for SUN. The difference is that in the case of SON, the global symmetry you have is discrete, that you can identify. And in the case of SUN, it's continuous. And I'm saying, I'll tell already from the beginning, how is that helpful? It turns out that the global symmetry, and the order parameter is actually something built like a baryon. In other words, it's the generalized antisymmetric tensor. And when you take the limit n goes to infinity, we know from Skirm models, other situations, it's not a simple object to handle. So the way we see that the symmetry is indeed persistently broken is by finding the Goldstone boson associated to the breaking of the symmetry. And indeed, we find at all temperature a massless particle. So this is the general structure. There is a flavor group, there is a gauge group. You find the conformal manifold, which using the Banks-Zaks analysis, which puts constraints on where the couplings have to be. You go to various points there, and you try and calculate effective potentials. Now, what do you expect of the effective potentials? Maybe I again invite you to the papers. I think the time is too short to explain. But here, this is a statement of the fermions in the one case of the SO groups, they are Majorana fermions. In the case of the SU group, they are Dirac fermions, and this tells you which fundamental representations they are of which group. The main thing is, when you write down the potential, it has in it two terms. It has a quartic term and it has a quadratic term. So when you look at the non-zero temperature, you induce the quadratic terms. When you are at zero temperature and you have a CFT, you don't have the quadratic terms, of course, because they carry a scale. But they can come in once you put in the temperature. So what do you need basically to look at? You need to find where you are on the Banks-Zaks manifold. Then you need to be sure that your phi to the force couplings of various types stabilize the potential at infinity. And then you ask yourself, do you have at the origin some negative second derivatives, which means you have terms which would destabilize at the origin. And if then you are sure that far away you are stable, near the origin you go below zero, then you're going to have somewhere a breaking. And this is the way we did the analysis. So to ensure that you are stable and to see that somewhere in some regions you are not stable. So this is the general, again, description of the models. I will skip all of that. I will just, these are the global symmetries. I will mention this I told you, this is the operator, which is determinant of the phis. These are scalars, but still you call it baryon. So it's the general antisymmetric form. And this is the order parameter, which one is checking. And as I told you, the cleanest way to see that is to see the Goldstone boson associated with that. But in the effective potential, which if it gets a non-zero expectation value, so would the determinant of phi. Where do you find here the terms? This is an example. So for t equals 0, as I said, no flat directions, unfortunately for me, but there is this potential. And then this is one point here in the range of couplings which defines these systems. And then at temperature 0, there is no symmetry breaking. But the moment you turn out the temperature, you get a negative term near the origin. You are stable at infinity. Here, notice the 0 is here, not here. So you go below 0, and you have a breaking of the symmetry. And therefore, at the end, the global parameter also is non-zero. And you have a persistent symmetry breaking, because the moment it happened at one temperature, it will be there at all temperatures. So to summarize in this part of the talk, I would say very briefly discuss the 3+1 gauge theory example. I told you that these models have conformal manifolds in their coupling constants which are available. This for n equal infinity. Under appropriate condition, and you look at some interval of these, it's not everywhere, it's on an interval somewhere on the conformal manifold, you can see the phenomena of persistent symmetry breaking. It's there. And the broken symmetry is U1 in the case of SUN groups, and there you can see the massless particle, which is the important issue. You can also see how the W masses are there, and they don't deviate from the standard model in that case. Then I didn't show, but I told you that there is also a marginal operator built only out of scalars, which has the properties that at the infrared, in the presence of this operator, in the infrared, there is symmetry breaking. There's no symmetry breaking, but then as you increase the temperature, actually the inverse symmetry breaking phenomena starts, and it's persistent. It lasts up to all temperatures. Okay, maybe about future directions, I want to point out to some work done by Kai, Dimarsky, and Smolkin. they ventured into, they are tempted by the 3. They want to go to 3. Now, as you know, in 3, there is a theorem by Coleman, which in particle physics we are less familiar with it. We are used at him in 2 dimensions, but there is a high temperature theorem of him, Merwin, Hohenberg, also applying to the impossibility of breaking symmetries at finite temperature. And they try to go around that. And the way they do that is, of course, usually you violate one of the axioms which were done in the no-go theorems. And the axioms they dare to violate is locality. So they have a very high derivative, they have higher derivative terms, and they claim that they have persistent symmetry breaking in that model, also in 3 dimensions. I think that's out of the future direction. So I will end and say Mazal Tov.
As we are running late on time, maybe one urgent question.
Can I, since there's no other question, so is there a case where a non-SUSY protected conformal manifold really exists at finite n? Do we have such?
In what dimension?
Yeah, well, preferably in an integer dimension.
Well, 2, are you asking? Do you ask about 4?
Not 2, of course.
So you're asking about 4. Okay. I didn't enter into that. I would say we don't have, there's no positive indication that I can say that what we work survives. We don't have a counter indication, but we have no reason at this stage that to say that the large n, finite but large n will maintain the result. I don't know about that. But to me, the curious thing is, are they no-go theorems? Okay, I mean, so I think we pushed it higher than what was expected before, especially fractional dimensions, also finite n, not infinite n. So large but finite n. So are there eventually no-go theorems? My hope would be that there are not. But if there are, they are interesting, and it would be nice, I think, to find them. I'm sure people have tried from time to time to find such no-go theorems, but I'm not aware of the success. Are you? No. So the answer to your question was, as of now, no.
Okay, I suggest we thank Eliezer.